well, hello, everyone. Welcome to the first technical session of the day or night, depending on where you are in the world. We have 4 very interesting talks for you today that have applications in a wide variety of domains, from clinical trials to spatial dynamics and beyond. And we're going to go ahead and jump right in. But before we do, just a couple of housekeeping items. Each speaker will have roughly 15 minutes, a little bit less, to get their talk in with a Q&A if time permits. So please enter your questions in the chat or the Q&A function if you have any questions for our speakers. And in order to stay on track, rather than giving a visual cue, since I don't think the speakers will be able to see me when they're in, presentation mode, I'll just speak into the microphone to signal that there are 2 minutes left in an effort to end the session on time. So we're going to start with a talk by Amia Graye. Amia is a master's student in the biostatistics program at Johns Hopkins University. She holds a BA in mathematics from Georgetown University and worked as a postbac fellow in the Office of Biostatistics Research at the NHLBI, which is coincidentally where I work and where I had the great pleasure of working with her before she went off to graduate school. The title of her talk is Key Parameter Sequential Monitoring, Computing a Sequential Confidence Interval for the Mean, and discussing its variability amongst different distributions. So take it away, Amia.
Thank you, Ruba, for the introduction. Can everybody hear me okay?
I can, yes.
Yes.
Okay, great. So I'll just share my screen. Okay, so as Ruba said, I'm Amia Graye, and my talk is titled Key Parameter Sequential Monitoring, Computing a Sequential Confidence Interval for the Mean and Discussing its Variability amongst Different Distributions. I'm not sure why the outline slide isn't showing up, but we can just go ahead to the next slide. So, introduction, continuous monitoring of the mean. So, continuous monitoring is often used to detect if an empirical measurement is different from the target. And clinical trials of large scale can utilize continuous monitoring of the mean parameter to know when it's a good time to stop a trial or to continue monitoring. So the goal for this project that I was on was to address the uncertainty of parameter monitoring during a trial or clinical study by computing a sequential confidence interval for the mean if the data meets the stopping criteria. So through simulation, clinicians and researchers can be provided with a highly educated estimate of the stopping time for their studies based on margin of error values for an array of distributions. And for this study, I looked at 3 distributions: the Gaussian, Bernoulli, and exponential. So these 3 are very widely used in clinical trials for different types of data. But I do want to explore other distributions in the future, like the T distribution here at the bottom, and also the gamma distribution. So the first distribution we looked at was the Gaussian distribution. So the Gaussian model is a very popular choice for many clinical trials because of its simplicity and the use of statistical tools like the central limit theorem. So for this simulation, we did 2,000 simulations for each margin of error. And the setup was the mean was equal to 0. And we looked at standard deviation values of the square root of 1/2, 1, the square root of 2, 2, and 4. So the goal of this study for this distribution was for researchers who have monitoring data with this setup to get a confidence interval for the stopping time, which here we call tau, that can roughly suggest what confidence interval they would get around the stopping time. This is important because now we can see the variability of tau and make a better estimate of what the stopping time should be for your study. So the key findings for the Gaussian model. So this is an example of just what the data looked like for when the standard deviation was the square root of 2. So as you can see here, the confidence interval for the stopping time tau decreased as the margin of error increased. Looking at the table here, we start with a margin of error of 0.1 that goes to 0.3, and you can see how the minimum and the maximum start to decrease as the margin of error increases, which does make sense, since if there's more margin of error, that allows for a quicker stopping time. And as the standard deviation increased, larger margin of errors were required. So in this diagram, these were all of the standard deviations that we looked at. And as you can see, for each of them showed the minimum margin of error value that was used for that specific standard deviation. So when we had a standard deviation equal to square root of 1/2, the starting value for the margin of error was 0.05, and then for standard deviation of 4, the starting margin of error was 0.02. And the minimum sample size varied based on the standard deviation and the margin of error. So in this one, in the parentheses in this first column in the table, you can see I started with the minimum sample size of 5 or 10, but as that standard deviation did increase, the minimum sample size did vary and often increased as the standard deviation increased. And you can also see in the x-axis with the stopping time, kind of the variability between each of the standard deviations. It seems to get a bit higher as the standard deviation does increase. So the next distribution that we looked at was the Bernoulli distribution. So this is often used for trial with binary outcomes and randomization. So in this, we looked at 7 different values for the probability, and we looked at 3 different margin of error values. And similar to the normal distribution, we did 2,000 simulations for each. And the goal for this study was for researchers to be able to compute a confidence interval for the stopping time when they have data with these probability values or around it. So key findings for the Bernoulli distribution. This is an example for when the probability equaled 0.3. As the sample size increased, the margin of error did decrease. So as you can see here with the minimum sample size on the side, oh, sorry, I meant with the x-axis for the stopping time, the confidence interval for the stopping time tau decreased as the probability moved away from 0.5. And in this like array of histograms, I'm showing the probabilities for each of the ones that we looked at, all 7 of them, with only the error value 0.03. And this here one is for 0.5, and you can see as you go towards 0.5, the stopping time seems to increase in the x-axis. And this is because in the Bernoulli distribution, with the standard error, a larger sample size reduces the standard error, leading to a smaller margin of error. And as we can see in the tables, the confidence interval for the stopping time tau decreases as the margin of error increases. And like I was saying before, the probability moves away from 0.5 as the confidence interval decreases. And based on the standard error formula, the formula is maximized when the probability equals 0.5. So for proportions closer to 0 or 1, like 0.2 or 0.8, the product p times 1 minus p, which is the variance, is smaller, reducing the margin of error, and then since reducing the standard error and then reducing the margin of error. And the last distribution we looked at was the exponential distribution. So this is used a lot in clinical trials for time to event data. Using time to event data. And for this, we used 6 different rate values, and we did 2,000 simulations for each one. And the goal for this distribution, similar to the other ones, was to get a confidence interval for tau that can roughly suggest what confidence interval they would get around a certain stopping time. So for the exponential distribution, since the mean is 1 over the rate, the mean would decrease, sorry, as the rate is increased. And opposite to the normal distribution, the margin of errors for this distribution, the larger margin of errors were required for smaller rates. So in this example, I used lambda equals 1.5, and you can see how it starts with 0.04, but in this histogram here for 0.05, the margin of error starts with 0.01. So it's kind of the reverse for the normal distribution. And some key findings we saw here was the confidence interval for tau decreases as the margin of error increases. The smaller rates for lambda require larger margin of errors, which I explained before. And minimum sample size starts much higher due to variability in time to event data. So in this first column, the minimum sample size value, like you can see, starts with 30, ends with 50, but in the normal distribution, I started with 5 or 10 or 15. So because of the time to event data, there is higher availability. So you need to start with a higher minimum sample size value in order to get a good stopping time. So just comparing the different distributions, so a common trend I saw in all 3 of them was as the margin of error increases, the confidence interval for the stopping time tau decreases. And for Gaussian, smaller margin of error were used for lower standard deviation values. And in the Bernoulli distribution, lower margin of error there were lower margins of error closer when the probability is equal to 0.5. And for exponential, larger sample sizes, there were larger sample sizes due to higher variability. So some implications for clinical trials. Understanding stopping time variability is critical for trial efficiency. And tailoring the error rates and sample sizes based on the type of distribution and study design is very important, so that you can stop when the trial is sufficiently completed, or you can know that this data is going to run the trial too long and it's going to use too many resources. So we may have to approach how to collect the data in a different way. And there needs to be a balance between early stopping and ensuring accurate, interpretable results. Because if you stop too early and you don't really have the results that you need, then that trial would have been all for naught. And if you go too long, you may waste resources and other people's time too. And so in conclusion and some future thoughts, estimating stopping time helps optimize trial designs. Simulation studies provide actionable insights for trial planning. And in future studies, I would like to explore other distributions in trial designs. Thank you for listening.
Thank you, Amia. Great talk. I don't see any questions in the Q&A or the comments or the chat box rather for now. But if the audience has questions that, come to mind, please feel free to use those features. Thank you, Amia. We're going to
Thanks, Ruben.
Thank you. Move to our next speaker, who is Eugene Hwang. Eugene is a PhD candidate at the Graduate School of Culture and Technology at KAIST, the Korean Advanced Institute of Science and Technology, where she's a researcher in their visual cognition lab. She has an MS from that university, as well as a dual BA in Media and Communications and Business from Korea University. Her current research is on the use of eye tracking and EEG methods, and the title of her talk today is "What is Your Focus? Gaze Data-Based Research and Attention Dynamics." So take it away, Eugene.
Thank you for your introduction. Okay, can everyone see my screen and hear my talk?
Yes.
Okay. So, hello, my name is Eugene Hwang, a PhD candidate at Visual Cognition Lab of Graduate School of Culture and Technology at KAIST. Today, I'll be giving a talk on what is your focus, gaze database research and attention dynamics for International Day of Women in Statistics and Data Science. As I was introduced, I earned my bachelor's in media communications with a dual degree in business, but now I am studying human-computer interaction and cognitive science. My journey from studying media and business to pursuing PhD in engineering at KAIST was unexpected, but it now seems like a natural progression. I always too wanted to study the ever-changing media landscape, and we consume media content and interact with media services every day, and I wanted to be at the front of the change. So to begin my journey, I applied to the School of Media and Communication at Korea University. During this time, I worked as a camera crew member for TEDx talks at our school. I was cramming to edit the videos that had to be released on the TEDx website in 2 days, and while I was editing, I realized that I had developed a mental eye of the viewer and was editing accordingly with how the eye moved along the talk. The hands-on experience in media production gave me a realization that how we perceive media stems from our cognitive processes, which are reflected by our physiological changes such as eye movements. My fascination with capturing attention in content creation led me to delve deeper into the concept. The word attention is thrown around everywhere, but I wanted to know what it was beyond its casual usage in various disciplines. I wanted to understand attention quantitatively and its profound impact on perceiving the world around us. Realizing the need to transition from mere user of media to technology leader, I took a leap and pursued the graduate degree at Visual Cognition Lab in Culture Technology at KAIST. My research focused on visual attention in dynamic media landscapes, and my goal is to leverage this understanding in real-world settings where attention plays a critical role. As XR devices becoming more increasingly popular, gaze-based data are becoming more readily available for collection. Eye trackers embedded within VR devices are quite commonplace now, but the usage is limited to gaze-based interaction, foveated rendering, and avatar animation. Despite the growing popularity of these devices, there is still a notable gap in research due to the abundance of data but the lack of defined components. The study of attention is crucial in dynamic media landscapes, as attention precedes all our other cognitive processes and is central to how we understand the world. Eye trackers are commonly used in attention studies as it proves data with high spatial and temporal resolution. However, even in attention research, it is centered on locus of attention rather than the subtle components that form our intricate cognitive process. As we know from our daily experiences, we know that looking does not mean we are paying attention. For instance, the professor will agree that most of the students are staring at the screen, but they're thinking what to eat for lunch. My research has been centered around defining the attention characteristics and the indices that indicate different attentional states within gaze-based data, collected using eye tracking methods. During my master's, I co-led a study on defining the cognitive characteristics of intellectual disabilities in virtual reality. It was a joint study with IDWSDS. It was a pivotal project where I had a hands-on experience on how important study of attention was, and it sparked my desire to study attention for the betterment of humans. Due to limited resources and for easier access, there's a growing market for a virtual reality-based occupational training program, especially for people with intellectual disability. And this project involved identifying the attentional features of intellectual disability that could be utilized in their VR-based occupational training programs, such as providing visual cues to guide the next step to making cappuccino, that will help them find a job and gain independence. So we used the Posner cueing paradigm and applied it within the virtual environment, with various attentional cues of visual, auditory, and tactile modality to see the attentional characteristic of the intellectual disability group. Our results show that intellectual disability group have a modality-driven attention mechanism, where they showed deteriorated top-down attention, especially for auditory and tactile cues. This implies that it might not be effective means of attention guidance for virtual reality for intellectual disability group when you use auditory or tactile cues to guide attention, and it'll be more effective to use the visual cues. Also, the attention processing does not follow the history-driven patterns, where repetition showed worse effect for intellectual disability. This experience provided crucial insights into how different humans are in allocating attention within complex virtual environments, according to their individual traits, and underscored the potential for virtual reality for personalized learning and human enhancement applications. During my doctoral research, I have been working on investigating and applying gaze-based data, aiming to understand what attentional state they signify and how they can be utilized. First, we investigated the pupil-based components based on attentional states. The attentional fluctuations were measured and defined using the GRAD CPT, and we varied the difficulty of the task using MBEC paradigms. The corresponding gaze changes were measured with an eye tracker while the participants engaged in this task. GRAD CPT is a well-established cognitive psychology experiment paradigm where the participants give repeated responses, and the variance in the response time shows whether they were in the zone or out of the zone. We defined the attentional states based on the response time variability, with higher variances above the median being out of the zone state, and analyzed the ocular characteristics within each time epoch. The results revealed slower response times and slower signal detection sensitivity, D', which replicated the previous findings. Interestingly, there was a significant difference with pupillometric components such as longer peak latency and longer peak-to-response latency. These findings indicate that cognitive process slows down when focused on the task, zones out. Thus, the pupil takes longer to reach the peak. And the motor reflex to the cognitive process slows down even further, resulting in slower peak-to-response latency. This tendency was consistent even in high cognitive load conditions, as well as low cognitive load tasks, as evidenced by both physiological and behavioral components, which implies that no matter the difficulty, our pupillometric responses slow down when we zone out. For real-world applications, I focused on how we each have different focus of interest. This is actually a gaze plot of two participants when watching a lecture video. When learning, some will prefer looking at the lecturer, while some will focus on the material. With my background in media, I proposed a new method of automated editing by just watching a virtual lecture, which will provide customized learning experiences that are tailored to their attentional patterns. Using a deep learning Meebles model, I separated the areas of interest of a lecture video and assigned the corresponding video shots for the areas of interest. And the percentage of the distribution of attention was then weighted with the fixation duration and interpolated along the lecture timeline. This data was then applied to video editing by using Python library MoviePy. In short, using the eye tracking data of the viewer, the video was automatically edited according to their attentional patterns. The results showed near professional video quality with a fraction of the editing time, and the viewers could not differentiate it with the professionally edited videos in terms of learning experience and video quality. Through this research, we showed the possibility of reducing the labor cost of video production by utilizing attention data, and that when the video is customizable to each learner's attention patterns, It is indistinguishable from learning with professionally produced materials. This was simply based on spatial attention, and I believe by defining more precise and subtle attentional indices that are shown on gaze data, the learning experiences can be even higher than uniformly edited videos. So throughout my academic journey, I have devoted myself to studying the biological indices of human attention and exploring their practical applications for the betterment of our media experiences. I believe that my research has infinite possibility of application. For instance, for education, we can provide tailored learning experiences, as mentioned just before. And for safety, we can prevent accidents through zonal detection in hazardous environments such as driving or at construction sites. And also for accessibility, we can provide appropriate aid according to the attentional state of the user. I'm currently working on defining the gaze-based indices of attention in XR environments. And in the near future, I am ready to transition to the next phase of my research, crafting real-world solutions to bridge the digital gap for marginalized communities. Currently, there's a severe digital divide with the older generation and daily digital usage. And after my PhD, I plan to utilize my research in defining the attentional state of users, and especially for the older population, and develop a real-time attentional aid for senior users with augmented reality, which would provide guidance in navigating through the digital landscape when they start feeling lost. As I continue to push the boundaries of our understanding of attention and its practical applications, I'm excited about the endless opportunities to understand and enhance human experiences. I strongly believe that the key is to focus on what you want to do, and the method will follow. Do not shy away from your goals because you're scared that your background is not fitting or good enough. Because when you're focused on something, it means that you are meant to pursue it. Thank you for your attention.
Thank you, Eugene. That was a really, really interesting talk. I'm just checking to see if we have any questions. And it looks like we don't so far. But that was really cool, and I can see how that work can be extrapolated to other areas as well. I was thinking maybe other cognitive areas, not just attention. So that is very, very cool work. Thank you, Eugene. So we're gonna move on to our third speaker. All right, so our next speaker is Mongju Jeong. Mongju is a PhD candidate in statistics at Seoul National University, where she also earned her master's in statistics. She holds bachelor's degrees in both mathematics and applied statistics from Yonsei University. She's currently a researcher in the Spatial Statistics Lab led by Dr. Chae-young Lim, where she works on spatiotemporal modeling and clustering. The title of her talk is Exploring Spatial Dynamics in Regression Coefficients, a Bayesian regularization method with clustering. Go ahead, Mongju.
Thank you for introducing me. I'm Mongju Jeong from the Seoul National University in Korea. I'm very delighted to have the opportunity to present my work, which is a collaboration with my professor, Chae-young Lim. The title of my presentation is here. In spatial regression, we work with data that collected different locations, each with its own response and covariate vectors. The main question here is, how do we incorporate latent spatial information into our model? One way is to add a random spatial effect or use a spatially varying intercept to capture this. Another way is to use a coefficient that changes based on the location. But this method can be tricky without making some assumptions about the coefficient. This is especially true when the number of unknown coefficients is bigger than the number of data points we have. To solve this, we make assumptions like smoothness in the coefficients, involving methods like geographically weighted regression or spatially invariant coefficient models, as well as consideration for sparsity and clustering patterns. So in our model, we use assumptions like sparsity and clustering patterns to identify the key variable that affect the response and to explore the spatial clustering of their effects. This leads to the proposal of the Bayesian regularization spatial clustered coefficient regression model, BRSCC model. By using the same indicator variables that shaped the prior model for both regression coefficient and cluster configuration, we can achieve both goals at the same time. The spike and slope prior, which uses the indicator variable, offers a probabilistic framework that allows the sum coefficients to be exactly 0. The posterior samples for each coefficient also provides a way to directly measure uncertainty. Before introducing the model equation, let me explain some of the notation used in the description. First, we call A0 the true activated index set, which includes the indices where the associated regression coefficients are not 0. For each non-zero coefficient, we assume that the spatial variation of the effect is divided into separate, non-overlapping clusters. This means that the effect of each vector changes across different clusters, but stays the same within cluster. For each covariate index L, the curly capital C represents the cluster partition of the L's coefficient, with KL denoting the number of clusters. The set of beta L1 to beta LKL represent distinct coefficient values for each cluster. If coefficient index is not included in the activated index set, it means that there is only one cluster and the coefficient is 0. Let's use yi to represent the response at location I and xij for the j's covariate at the same location. If site I is in the intersection of C1 I1 through CP IP, this means that the regression coefficient for the j's covariates at site I belongs to the ij's cluster. So the regression equation can be written as this follows, and where epsilon I follows the normal distribution with the mean 0 and variance of sigma squared. Now, denote C as the total cluster partition of the N observation and large G, J, with the KJ cluster centers in CJ. We use this Voronoi tessellation method to divide the space into clusters, assigning each point to its nearest cluster center. The distance between the observation I and cluster center GJ typically measured using Euclidean distance. Now, I will introduce the prior settings for the unknown cluster configuration and regression coefficient. To perform variable selection, we introduce a random indicator variable gamma j to decide whether the j's coefficient beta j is equal to 0 or not. We use an independent spike and slope mixture prior on beta j, where the gamma j equals 1 indicates that the covariate has no effect on the response. For the exclusion indicated gamma j, we impose a Voronoi distribution. As for the variance parameters, we assume an inverse gamma distribution. We set independent priors for the cluster configuration coalescing of each regression coefficient. We think that the cluster setup for the J covariate CJ is made up of three parts: the variable selection status gamma j, and the cluster number of cluster kj, and the cluster centers gj. The prior distribution for the number of clusters is made flexible to cover different cases, including when there is only one cluster. If gamma j equals 1, the coefficient for that variable is 0, meaning that it does not have a cluster structure, which means the number of cluster to be 1. However, if the variable j is included in model, the prior assumption for the number of clusters kj comes from a Poisson distribution with a mean of 1 minus dj. In the case, when dj is small, the influence of the prior becomes weaker. Lastly, given the number of clusters, the prior assumptions for the cluster centers assumes all possible cluster centers are equally likely. Since the number of parameters changes with the number of clusters, we use Green's reversible jump MCMC algorithm. This allows us to move between models with different number of cluster parameters by introducing an auxiliary variable u and a diffeomorphism q for a smooth transition between models. This algorithm suggests adding or removing parameters which are accepted or rejected based on a probability rule to maintain balance and stability. The metropolis-testing screen ratio, alpha, includes factors like the ratio of likelihood and the ratio of priors and the ratio of proposal distribution and a Jacobian term, which is adjusted for changes in the parameter. To make it easier to explore different models for selecting variables and detecting hidden clusters, we simplify the calculation by using a collapsed posterior distribution. This means that we remove the need to calculate beta in the main step by integrating out of the distribution. Instead, we focus on the remaining parameters during the RJ-MCMC process. And later on, we can generate a sample of beta separately from its full continuous distribution. This method helps improve the efficiency of the algorithm. We propose two types of reversible jump moves for each covariate to explore the cluster configuration space effectively. First, we introduce the select and delete move. The select move adds variable to the model, while the delete move removes them, helping a pair of jumping moves helps adjust which variable are included in the model. Second, for the active covariate, we use burst and dash moves. The burst moves create new clusters, and dash move eliminate existing clusters, updating the cluster configuration as needed. So here's how the algorithm works, with an additional step included. In each round, we randomly select a covariate index and then decide whether to perform a select or delete move, depending on the current gamma value for the covariate. After making this variable selection status within the variable selection model, we update either the cluster configuration or the parameters. If the updated gamma value is 1, indicating that the coefficient has no effect, we proceed by updating only the parameters without altering the cluster configuration. Finally, we need to make inferences from the MCMC samples we obtained. But since each iteration produces different cluster structures, a method is required to decide on the final configuration. We estimate the clustering and variable selection parameters gamma, k, and gk using a model selection method, while the remaining model parameters are determined by the posterior mean or median. First, we estimate the gamma parameter using posterior mode to determine the variable selection. Then we look at the most frequent cluster numbers observed in the samples and use this as possible options for the number of clusters. Next, we compute similarity matrix SS, which shows how often two sites are grouped together across different iterations, and applying spatial spectral clustering to finalize the cluster structure for each option, K. In the end, we select the best model using Bayesian model selection criteria. For the simulation, we first randomly select 200 locations within a square domain. Then we create variables that are related to each other, both in terms of space and between different covariates. This setup mimics the patterns we often see in real world. Also, we consider several scenarios to show how effective the algorithm is in different situations. The first setting tests the effect of different noise levels, while the second and third setting compares the result with standard OLS regression and some variable selection approaches.
2 minutes, Mongju.
Okay. We compared our method with yes, the simulation are repeated 100 times we evaluate the simulation results using several metrics, the MSE and the true positive discovery and the number of false positive discovery and the Land index. Most of them may be familiar, but the Land index is used to check how accurately the actual clusters are identified. A value near 1 is ideal. We compared our method with the SCC model, which finds clustered coefficient without variable selection, and the SCC through VS indicates the model applying SCC only to the true active coefficient. Our method consistently identifying two non-zero coefficients and rarely activates zero coefficient. It also outperforms others in accurately estimating regression coefficient and clustering patterns. Additionally, in the basic setting, our method provides regression coefficient estimate as accurate as those from the OLS approach. In scenario 3, we found that our method is superior to other variable selection approach in excluding zero coefficient from the model. So throughout the reverse subjump MCMC algorithm, we are able to perform variable selection while simultaneously exploring the spatial structure of the selected coefficients. The simulation results demonstrated the effectiveness of the algorithm. As for future plans, I've left the stage of applying the algorithm to real data. That concludes my presentation. Thank you for listening.
Thank you, Mongju. That's really interesting. And I'm just thinking along the lines of my work and how, you know, this type of research could be used in spatial epidemiology and probably has many other applications. So very interesting work. Thank you so much.
Mm-hmm.
We're going to move on to our last speaker of this session, who is Samuel Lawrence, another familiar face to me. Sam is an undergraduate student at Hood College, where he's pursuing a BA in mathematics as well as a BS in computer science. This past summer, Sam worked at the Office of Biostatistics Research at the NHLBI under the guidance of Dr. James Trendle, where he developed an R package that implements win time methods. The title of his talk is Win Time R Package for Analysis of Time to Event Data in Clinical Trials. And the floor is yours, Sam.
All right. Can you see my slides?
Yes. Yes.
Okay. Okay. So, like Ruba said, I spent the summer working with the Office of Biostatistics Research at the U.S. National Heart, Lung, and Blood Institute. There, I developed an R package that implements new methods of analyzing clinical trial data. And during this presentation, I will introduce a few of the methods and give an overview on how to use the package. So the example that we're going to be considering is the NHLBI HF action trial. So here, heart failure subjects were randomized into either the treatment arm or the control arm, where the treatment arm was assigned to exercise training and the control arm was assigned to their usual care. And the primary outcome of this trial was the time to the first of either hospitalization or death. Now, the issue with this as a primary outcome is that a statistically significant result might not translate to a meaningful treatment benefit, because it's possible to have a treatment that provides benefit on hospitalization but harm on death. And with this as our composite, the test results might still look good based on this composite. So the first method I'll introduce is called the win ratio. Now, this is not a method that was developed by my group, but I think it's useful to help get us thinking about win statistics and the types of comparisons that we're going to be making. So the win ratio works by organizing subjects in a trial into pairs, with one person being in the control arm and one person being in the treatment arm. It compares them on the most severe event first, and if inconclusive, it will move on to less severe events based on a predefined hierarchy. So in our example, if we look at a random pair, if the control subject dies before the treatment subject, that is an automatic win for treatment. If the treatment subject dies before the control subject, that is an automatic loss for treatment. If neither person dies, then we move on to hospitalization and try to compare them and determine a winner that way. And then our win ratio is simply our wins divided by our losses. Now, this reduces, but it does not eliminate the issue that I highlighted in the previous slide. It fails to capture each impact. It fails to capture the impact of each component of the composite, and therefore fails to capture the entire experience of the patient during the trial. And it also leads to many tied pairs due to censoring or patients dropping out of the trial early. So win time is the title of the package that I developed, and it is also the foundational idea of all of these new methods. So the idea is that treatment effects should be measured by the amount of time the treatment arm spends in a better state than the control arm. So we want to look at how long the treatment arm is healthier than the control arm. And there were several new methods introduced by the Office of Biostatistics Research that use this idea of win time in different ways. And these tests do result in tests where a significant result does actually imply a treatment benefit. And unlike the win ratio, it accounts for the entire experience of the patient because it captures the impact of each component of the composite. So the first method that I will introduce is called the win time ratio, or WTR. Now this works in a similar way to the ordinary win ratio, except wins and losses are determined by the amount of time the treatment subject spends in a better state than the control subject. So if we look at our graph here, we see that red represents the treatment subject and black represents the control subject. So, and we're looking at hospitalization and death. So we see that after 1 year, the treatment subject is hospitalized. And then after 1.5 years, the control subject is hospitalized. So for this 0.5 year interval, the treatment subject is in a worse state than the control subject. So we are accumulating a negative win time for treatment. And then after 2.5 years, we see that the control subject dies. And then after 3.5 years, the treatment subject dies. So for this year-long interval, while the treatment subject is still alive, we are accumulating positive win time. So this results in a win time difference of 0.5 and scores a win for treatment. The next method I'll introduce is called the expected win time, or EWT. Now, the idea behind the EWT method is to measure how well we can expect the average treatment patient to do compared to the average control patient. So rather than doing this pairwise comparison between individuals, we're comparing the treatment arms directly. So we do this by fitting a Kaplan-Meier model to estimate the state probabilities for each arm. From these models, we can construct what's called an expected win function of the treatment arm, and then integrate that function to get the expected win time of the treatment arm. This allows us to increase power by comparing arms rather than individuals, and saves us a lot of time and computational power compared to the pairwise methods. So to demonstrate, we have two graphs. The top graph represents the estimated control arm probabilities of being in a certain state at a given time. The bottom has the same thing but for the treatment arm. So if we look closely at the graph, we see that according to our model here, if you were in the control arm, after 0.5 years, you have a 20% probability of being hospitalized. If we look at the treatment arm, the estimated treatment arm probabilities, we see that after 0.5 years, you have a 20% probability of being dead. So for this year-long interval, we expect that the treatment arm will be losing to the control arm. Although we see that the control arm probabilities of hospitalization and death spike, where the treatment arm probabilities mostly stay where they are. And this is reflected in our expected win function that is constructed from these graphs. And again, integrating gives us the expected win time of the treatment arm. So it's how well we can expect the average treatment person to do against the average control person. The next method I'll introduce is called the expected win time against reference, or EWTR. Now this works in a similar way to the method that I just described, the EWT method, although we only fit the Kaplan-Meier model to estimate the control arm probabilities, and then we construct an expected win function for each participant in the trial, integrate that to get an EWTR value for each subject. And then other methods that are included in the package are here. I put a link to the paper in case you want to check them out, but these are just slight modifications of the methods that I already described. And then now onto the R package, we have 3 available functions for use. We have the main calling function titled win_time that runs any of the methods that I described and any of the methods in the paper on observed and possibly resampled data. We have KM that fits a Kaplan-Meier model to estimate the state probabilities for each arm. And then we have Markov, which is a function that fits a Markov model to estimate the state probabilities for each arm. So the required parameters for the main calling function win_time are the win_time method that you'd like to run, a matrix of event times, a matrix of event indicators with 1 representing an observed event and 0 representing censoring, and then treatment, which is a vector of treatment arm indicators with 1 representing the treatment group and 0 representing the control group. Optionally, you can add a matrix of covariates for certain methods. You can specify whether you want to use a Kaplan-Meier model or a Markov model. It is set up to run defaults, but you could override that if you wanted to. You could do the same thing with the resampling technique. You could choose between bootstrapping or permutations. You have to give it the number of resamples that you want, and then optionally, you can enter a seed for replicability and resampling. Markov and KM have the same parameter list, so we would need the size of the control arm, the size of the treatment arm, the number of events defined in the hierarchy, and then the same matrices of times and indicators from the main calling function. And then this first link is to the paper that was published by members of the Office of Biostatistics Research. And then the second link is to the CRAN page for the win_time package. And pending any questions, that is all I have. Thank you.
Thank you, Sam. Great talk. I don't see any questions in the Q&A or the chat. Cynthia says, cool package. Thanks for sharing.
Thank you.
And I'm definitely excited to use it in the clinical trials that I'm working on. So looking forward to it. Any other questions? I'll open up the floor before we hand it off to the next session. I don't see any raised hands. Cynthia's asking, tell us about your package making experience, complex or fun?
Complex. All the code
Complex.
took like an hour to write and a week to fix.
Wow. So there was a lot of debugging involved, I imagine.
Oh, yeah.
Well, I'm sure it'll be very useful for James and for you and for all of us at OBR. So thank you for working on that.
Thank you.
All right. Thank you all for such great talks. I'll just ask Cynthia if you have any closing remarks before we hand it off.
Thank you very much, Ruba, for chairing this session. I think we can take a moment's break. We're going to invite the other panelists in and around. Encourage folks to stick around for the next section. We're going to stop the recording and get the next one ready.